Very good. So this week we're very happy to have Anupam Mazumdar all the way from Groningen, and he's going to tell us about witnessing quantum gravity via entanglement.
Thanks, thank you, Adam. So first of all, thank Bob, Gautam, and Dane for inviting me here, and it's really a great pleasure to be back in Chicago. So I have to say that I mean, we kind of like introduced this. Actually, I was not in this field at all. I was completely in a different field, doing particle cosmology and gravity, very esoteric gravity stuff. But in 2017, I got introduced to this subject thanks to my collaboration and one of my collaborators here, Andy Geraci. And since then, actually, it has somehow sunk me in, because the more and more I realize the problem, I realize that it's becoming more and more interesting, and many of the things have not been solved. And so, it's kind of like I've become like a PhD student, so I'm learning, like many other colleagues of mine. So good. So I think the talk. So maybe I just first do I have a pointer? Yeah. Good. So I think the gist of the talk is actually in this sentence. So observing the quantum nature of a system is not limited to evidencing order H-bar correction. If you can see H-bar correction, that's fantastic. I mean, you would love to see that in an experiment, but it's not limited to it, because the question we have to ask, and it becomes pertinent, especially in the case of gravity, and you would realize why it is so pertinent, because it hinges upon some task which classical system cannot mimic. So it's a classical versus quantum, and that's what you want to understand, the difference you want to understand. And so this is what we actually proposed way back in 2017. There was also a paper on the same day by colleagues from Oxford, and independently, Bob has been working quite in a slightly different approach, but it seems that there's some connection. His approach has been much more fundamental, putting fundamental limits on gravitational decoherence to a quantum system. Has some connection to gravitational memory, which Gautam and Dane would be perhaps much more able people to discuss with all of you. And so they have been working on, quite consistently. They have written papers, and paper first I came to know about Bob's work way back in 2018. So okay, so I will just tell you a little bit of the progress, what are the challenges, and how can we overcome some of these challenges. Okay, so the plan, of course, is to go for an unambiguous test for the quantum nature of gravity in a lab. But as soon as I say unambiguous, I put too much pressure on myself. So I have to look at the fine print. So the fine print would be to go for as much as possible. Maybe you will not be able to beat it completely, but go for as much as possible, a loophole-free test for quantum nature of gravity. Okay. So, but before I even speak of quantum nature of gravity, I have to be very clear about what properties am I looking for in a system. Because if you want to understand certain aspects which is purely quantum, you must deal with quantum quantities, quantum properties. And the two quantum properties which cannot be mimicked by any classical physics is, say, quantum superposition and quantum entanglement. And these notions have been there since, from the undergraduate days, we have understood these concepts. And I'll introduce you this protocol. We call it quantum gravity-induced entanglement of masses. And then I will talk about two protocols. One is putting superposition, quantum superposition, spatial superposition of masses, massive systems. And the other one is equally interesting. It's actually the analog of light bending experiment. You can do it in a laboratory, but now instead of looking at the light bending, the deflection angle, you're looking into the entanglement properties between, say, quantum system and the photon. And I'll tell you what are the challenges. So there are many, many challenges. I mean, they're extremely challenging task because it's not easy. As we know that detecting a single graviton is extremely hard. Dyson's argument comes on your face that you would require, you cannot do it at all. So a single click of graviton is impossible to detect, but somehow through entanglement, can you see some of its properties or not? So that's the challenge. Okay. And please feel free to ask me, interrupt me anytime. It's more like a discussion as well. Okay. Now, actually, gravity is so rich that, I mean, also because of various reasons, it's also a philosophical subject. And so many people have many opinions. So maybe someone would say that on a classical level, I mean, gravity is, I mean, on a macroscopic level, gravity is inherently classical. And one of the biggest proponent perhaps would be none other than Penrose himself. He would say that, on a macroscopic systems are inherently classical, space-time is classical. And that's pretty much, he's okay because there is no experiment to take one view or the other. Some people I have come across who say that, oh, the first term is pure, the Newtonian potential is classical, then because you don't see any H bar. So it's just classical. The rest of them, when you start seeing H bar, and this is the kind of term which you would write down perhaps in effective field theory. You would get first the Newtonian term, then of course momentum dependent terms, and then eventually at one loop you will start getting H bar correction. So they would say that these terms where there is no H bar, they are inherently classical. It's not quantum. So no way you can see any quantum feature, because if you compare these two terms, you see that G is very small number, H bar is very small number, and when you're talking about the masses which we are dealing with, it's very suppressed. Turns out to be 1 part in 20. And it's almost like asking that, yeah, if I do that LHC experiment at TEV, can I go all the way to 20 orders of magnitude? The answer is not so easy. It is impossible, perhaps. So here also the answer is impossible, nearly impossible to reach 20 orders of magnitude. Yeah. So, and the third viewpoint, would perhaps many of our colleagues would take, perhaps in this room, everything is quantum. Whatever you see, all the interactions are quantum in nature. So the question is, even though there is no H bar, how could you extract the quantum property or quantum aspects of, from something which doesn't have H bar? So that's the kind of experimental challenge lies ahead of us. So let's go by the assumption. So the basic assumption I'm making is that all the standard, interactions, including this, well, we have for the standard model, we know very well, but the gravity, I'm assuming that inherently everything is quantum in nature. And the observation which I would like to make here, that there are two beautiful papers by none other than Asher Perez and Gisson, way back in 90s, they wrote. And so it's inspiration from these papers that even in the limit of H bar tending to 0, the quantum correlations do not vanish. Although it becomes extremely hard to extract that. If you want to, so when I say harvesting quantum property means I want to understand some observables, quantum observables, that becomes extremely hard.
So H bar is a dimensionful parameter. So
yeah.
What are you talking about when you say the limit H bar to 0?
I mean, H bar tends to 0, I mean, in a very loose way I'm talking about. Of course, what you are looking for is ordered parameter. And I'll come back to that order parameter. And that will be more relevant when I talk about the experiment. So I'm just comparing these kind of terms. Yeah. So, and based on Perez, essentially he gave quite a lot of very interesting ideas like witnessing, entanglement, and things like that. All came from effectively from these papers by Gisson and Perez. So key challenges. So what are the key challenges? So I'm just flashing this slide. Maybe I'll not go all the way talking all the details. May not have time, but if you're interested, you can always ask me. You want to achieve extremely pure quantum system for this. as much as possible, you want to reach the ground state of your system. Let's say harmonic oscillator. You are playing with harmonic oscillator. You really want to go to the ground state of the harmonic oscillator. Even if, and you want to disturb that harmonic oscillator, of course, because you need some ruler. You need to you need some measurement. And what is your measuring device? The measuring device will be some defect inside your system. So you need to understand that defect extremely, extremely well. And understanding the defect will tell you how well can you measure, how well is your ruler, essentially. So that means really you have to cool down the center of mass or cool down this entire bulk of the system, because at the end of the day, you are dealing with some material property. And you see that immediately something simple problem becomes even part of condensed matter physics. And then eventually it becomes part of quantum information, that how are you going to extract that witness? How you're going to read something. So this is this is the size of this ruler. From here, I want to extract some number. How would I extract that number? That goes into the witness. How big system am I playing with? Around 10 to minus 14 kilograms to 10 kilogram range. Special delocalization, I'm talking about something like 10 to minus 9 meter. I cannot go below that because that's your Bohr radius, 10 to minus 10. So if my delocalization parameter is so small as a nuclear size or atomic size, it's impossible for me to extract any information. So at best I can go 10 to minus 9 meters, nanometers, and you will see that for some parameter range, I need to go to 10 to minus 4 meters. And all these parameters are extremely, extremely challenging. No one has ever achieved it so far in any laboratory. And then perhaps some experiment, so in the experiment with the cavity, this photon, I want to understand the optical cavity, extremely, extremely high intensity beam, which is available. So right now, I mean, even many countries have this facility, especially because of you want to understand the fusion problem. So petawatt lasers are available, megawatt lasers are available. But the basic challenge is funding. That's the hardest problem. Anyway. So let's come back to the physics now. So classical versus quantum. So what exactly do I mean by classical and quantum? So classical means that, I'm standing here, you know, all the properties about me. You know, my hair color, my skin color, my whatever clothes I'm putting on, everything you know. But on the other hand, if I wear electron spin, then what happens is that I have this very interesting incompatible properties because sigma x, sigma y, sigma z, there's a commutation relationship. So I cannot measure simultaneously all of them at a given instant of time. I can measure only sigma x or sigma y, but this incompatible basis, the properties exist, and this is what makes the electron a quantum system as compared to any classical system. A classical system will never have that kind of property. But the important thing is that in any experiment, you want to understand correlation, and that's why at the end of the day, immediately you see that why entanglement becomes so important, because entanglement also is a certain kind of quantum correlation. So just to give you an example, very simple example. So I have got two systems. I have written this case form a quantum system, yeah, 0, 0, and 0, 1, and 1, 0, 1, 1 states. But here it's almost like a classical correlation. It's like thumbs up and thumbs down. My hands are classical. I have a classical correlation. Yeah. But I do not have that. I mean, if it were electron, I would have sigma x, sigma y, sigma z. All of them would be present. And that's not present in a classical correlation. You see that I have very specific kind of correlation I can build, but not all sorts of correlations which a quantum system will allow me to build. Yeah. So that's very simple difference. This is the kind of difference which we are looking at the end of the day in my quantum system, when I want to understand something about even gravity. And entanglement is a correlation which actually, I mean, so this is nothing but the Bell state. If you could see that the negative sign, the relative negative sign, is nothing but the Bell state. So in a Bell state, you have a classical correlation, yeah, like this, so the examples which I gave you, kind of like a classical correlation, but on top of that, it has correlations based on your incompatible basis. And that is inherent to quantum system, which is lacking in a classical system. Yeah. So there is a very interesting theorem And you will see part of the argument will be based on this theorem. And many of you are perhaps already know about it, especially those who are working on quantum information side. They're fully aware of this. I have heard talks in string theorists using this theorem nowadays. So the theorem states that no entanglement via classical channel. So what it means? So what it means is that suppose you have got a system, let's call it quantum system Alice, and you have got Bob, and Alice has a quantum apparatus. Alice is making some quantum observations on her apparatus, and Bob is similarly doing a similar experiment on his apparatus. But as long as they are interacting or exchanging information purely through a classical channel, then they are not going to enhance the entanglement. So suppose if they were, to begin with, if they were pure states, through classical channel, even if they interact or exchange information, the states of A and B are not going to get entangled. That's what the theorem tells us. And you can show it in various different ways, and many colleagues have involved their career, especially Bennett from IBM was the first person to come up with this theorem.
But the phones use the laws of quantum mechanics, so
Of
this
course.
must be an approximate statement.
I mean, this is imagine that's a purely classical line. I mean, yeah, of course, this is
What
just
does it
for,
mean, imagine there's a purely classical line?
I mean, don't take it so literally.
Well,
I
you
would
said
say
it's a
that
theorem.
through just, let's say, I mean,
What is a theorem without being literal?
okay, so what I mean is that Alice and Bob, they are interacting purely via classical channel. There's no quantum channel involved. Of course, you are inherently correct that there is no classical channel. That's what you would tell me. And I absolutely agree with you. After all, it's electromagnetic line, the electrons are flowing through. It is inherently a quantum system. So, of course, I mean, just take it not so literally, but a picture. Okay, so what I mean, we can make it slightly more concrete, and I think that's the direction which we are all moving towards. So what it means is that suppose you take two states, let's say that they are pure states, and I can do any unitary operation on A, I can do any unitary operation on B, and I can evolve that state to a state of A and state of B. But you see that just the unitary evolution on A and B are not going to make the states entangled. They will remain be pure. They will remain be separable. Of course, I mean, we're never dealing with a pure system because you're always interacting with some environment. So eventually you're dealing with a mixed system. And if you want to write down in terms of density matrix, and let's say that just for the argument's sake, your gravity is purely classical, then what's going to happen is that, so Aij is going to act on this quantum system. Imagine this is my quantum system. I'm doing it with some delocalization here. And so you have operators B acting on this system. And imagine that J is just because of the interaction which you have included. And let's assume this, for the argument's sake, is classical gravity.
So what is the theory of
Sorry?
classical gravity opposed to quantum system?
Absolutely, so it's a good question. So, I mean, let's say that, you do it semi-classical way. Just imagine the semi-classical, someone who doesn't believe that, because the whole point of doing an experiment is to convince someone who is agnostic about
Because if
it.
you have 1 over h bar multiply your whole action, everything is quantum.
You're absolutely correct. But the question is someone who
What is the
doesn't says that gravity is purely classical, and I take the average of my T mediums.
I don't know how to compute. You don't have a theory.
That's a fair criticism. There are a group of people who believe in that, and then they have their own prescription how to.
We are physicists, we're not talking about beliefs.
But very good question. So you need an experiment to convince them. Where is that experiment? So this is one
need to test
experiment.
the prediction of a theory.
I mean, so let's say that, yeah, I mean, as I said, that maybe a semi-classical treatment, I don't think there is, anything particularly wrong with that. You can do it. You can, now, of course, you have.
Just come back to the question. What do you mean by classic?
Um,
I have to clarify that.
Yeah, no, you're absolutely
If I
correct.
just take
So
my
it's
usual
classical,
active-
exactly. So what I mean by classical
Not
here is that when I can talk about some probability, classical probability, but out of that I will get some complex C numbers. I will not get anything beyond that. So in that sense, I'm talking about the classical system.
So is it fair to say, also in response to Clay's question, that what you mean by classical communication is that classical gravity acting on these systems is that I have a set of operators that act on the Hilbert space of particle A and a set of operators that act on the Hilbert space of system B. Now, that what operator I choose to act on each of those subsystems is completely up to me as an external classical person, right? So what I mean by classical communication, I think, is that based on some measurement I make of system A, I decide what unitary I'm going to act on system B. That will not generate entanglement.
Yeah.
To generate entanglement, I need some kind of unitary that acts on the tensor product Hilbert space.
Absolutely.
That has off diagonal
Off
terms.
diagonal contributions, yes.
Okay, and so that's why I don't generate entanglement.
Yeah, absolutely.
And I think similarly, the answer to Lian Tao's question is that what I mean is that I have some quantum systems A and B, and I'm going to determine what unitaries I act on each one by virtue of some classical gravity measurement.
Yeah. And it will become clear maybe within a slide or so.
What is a theory of classical gravity that does that?
So it does go on, sorry.
That's what Emo just described.
But you kind of by hand do some kind of average to get the energy momentum tensor to get the gravity.
Yeah.
You go classical
I
and
think
then you go to gravity.
you think if you start with a quantum theory, everything you do, you end up whatever average you do, you're going to get a quantum.
If you do it right,
Yeah.
yes. No, that's right.
I don't think you can modify it from the quantum action we already
It's
know
done
and
by hand.
You
it
have,
takes some limit. I don't think that's the
you take an example of
you are trying to say there's a radically new theory.
no, I'm not talking about
There's something called a classical gravity,
No, no,
not
I'm-
quantized.
Talking about it incorrectly.
I don't know what.
Let's put it this way,
theory is.
that maybe we are talking about incorrect theory. I mean, again, the question is that, when you want to do an experiment, you need to satisfy their criteria as well, those who don't believe in something. So that's the kind of like challenge.
Proof to them that they're
Yes.
incorrect.
But I'm exactly on your page. I'm not saying anything, I will not say anything different from what you are saying. Because even I would say perhaps classical gravity itself doesn't make sense given the fact that the rest of the system is purely quantum.
But there's a classical limit of quantum gravity, presumably, where the quantum states you're thinking about are highly coherent states with macroscopic numbers of quanta, where the quantum fluctuations are completely irrelevant to this phenomenon that he's going to study.
Yeah, but that theory, I don't think if you do test with that theory, you wouldn't see anything wrong. There's nothing wrong with that.
What do you mean by wrong?
Because I'm just taking I'm just saying you agree with the prediction of a theory with quantum gravity as well. Because you're just taking a theory that with gravity is quantized and taking a limit. So there's nothing, I think he's trying to say there's a contradiction. There's a new theory.
No, I'm not.
The new theory is called a classical gravity, not quantized.
Well, Emil's prescription doesn't tell you how to
Otherwise, I
calculate the fluctuations.
don't know what is testing. You're just testing some our known theory within interacting with gravity. I don't think it does anything special, right? So
Okay, let's see. And maybe the next slide perhaps will become a little bit more clear what exactly I mean by. But I'm to be honest, I'm not saying anything against what you are saying. I mean, I'm on the same page, except the way you treat classical gravity would be in a very ad hoc fashion. And suppose you do that ad hoc fashion, then what happens? That's what I'm saying. Okay, anyway, so one other thing which we, of course, you want to understand is that witness. So how you're going to witness this. And so witness is it's a very interesting subject by itself, which was first introduced by Gorodecki and his colleagues, and then also by Barbara Terhard. She happens to be one of my colleagues in Netherlands. And so the idea behind is that in any quantum system is, when you want to do an experiment, it's never a pure system because you always have some background, some interaction. So you're always dealing with a mixed system or mixed state. So given a mixed state, how can you extract whether the system is entangled or not? So that's the kind of question witness asks. And so witness is very, in a way, it's very geometric. As you know that for any convex set, you can always have the hyperplane which can distinguish various different properties. And this is what it does. So what it does is that it separates, so the witness, W is your witness, and for any given density matrix rho, what it tells you that it's not a necessary condition, it's sufficient condition. Keep in mind that if you find that trace of W rho is less than 0, then at least you know that you have detected some entangled state. Maybe not the whole set of entangled state, but some entangled state you have detected. And on the other hand, when you have trace of W rho is greater than equal to 0, then you cannot say, I mean, you know that there is a separable state, but there could also be some non-detected entangled states. So what it means is that, first of all, it is very much basis dependent, as well as it depends on how close, how finer witness can you choose. So it also depends on W. So someone can come up with a different W, and they can say that, hey, look, I can even touch this boundary. So this will be an even finer witness than this witness. Yeah. So witness is basis dependent. So that's one disadvantage. But as I said, that given an experiment, you cannot do it with an entanglement entropy because it becomes extremely hard to compute. You have to know your environment extremely well, but basis independent witness exists. So many times we use both. We use just to theoretically to see whether the system is entangled or not. We can use von Neumann's entanglement entropy or concurrence. But when it comes to really an experiment, I need to construct some witness. So one particular witness is kind of like this, which involves your sigma matrix, Pauli matrices, and you can construct many witnesses. Bell's witness was another witness you can use. So this is something which is an interesting witness, which we have applied quite a lot for this experiment, for this particular experiment. Okay, so maybe to coming back to Liang Tao's question, I mean, not particularly, I mean, I will shed any further light on his question, but I'm assuming here everything is quantum. So, but anyway, perhaps we'll give you the counterpart of it. So let's say that you're dealing with a quantum system, very simple perturbative quantum theory, not even gravity, is just any quantum interaction. So I have got Hamiltonian A. Let's assume them for the timing, they are even harmonic oscillators, HA, HB, and there is a small interaction term, HAV I'm adding. On top of that, let's say that I work in a Schmidt basis, a number basis. So initially I've started ground state. In presence of the interaction, the state evolves to something, because of the perturbation, it will evolve to some excited states, N and capital N I'm denoting here. But this state, you can write it down in a way, again in a Schmidt basis. So just rearranging the terms. So I'm writing it down like a product state. So this will be a product state, plus on top of that some contribution. And if this were completely zero, then you could immediately say that it's a product state. So separable state, it's like an example of a pure system. But if you find non-zero contribution, you see that these terms will cancel. So these are the leading order terms which you can expand. And as soon as you compute, and you can in principle compute these terms, these coefficients, just from your regular perturbation theory. It's the time-independent perturbation theory or time-dependent perturbation theory, you can compute these coefficients. And so here, so especially the lowest order contribution will have this kind of term. And if this term is non-zero, immediately you see that your final state, because of the interaction, is non-separable. It's a very simple way to show that in a quantum system, if you add any quantum interaction, it is inherently going to be entangled. Yeah. So the entanglement generation is automatic in any quantum system. And precisely this is the key for any quantum computer. way back in quantum computing algorithms as well. Chirac and Zoller, way back in 2000, I think, they had written this paper where they were thinking about ions, trapping the ions, and building an array where each of these ions are interacting by a Coulomb interaction. And it's and essentially you need an entanglement to build this very basics of any quantum computer. So we are doing something very similar now in the context of gravity. So exactly as you said, that LOCC, the classical channel actually doesn't exist. That's a fair comment. So then there has to be something which we should come up with, which is called the quantum communication. And that we all agree, we are on the same page. Everyone would perhaps agree that we can have a quantum communication or quantum interaction. So communication means here interaction. And the previous example which I showed you kind of illustrates this point. So let's say that we do a very simple calculation of something perturbative quantum gravity. Nothing fancy, just in the perturbative quantum gravity. If I take masses with momentum, and I assume that my perturbations are very tiny, HU is a very small quantity. I can quantize that. I can it is standard in a canonical approach. And I ask a very simple question that okay, I've got two masses. Let's assume these are two quantum harmonic oscillators. Yeah, I have switched on my gravitational interaction, my gravitational fluctuations. If I quantize the gravitational fluctuation, what will happen to my gravitational Hamiltonian? So as a consequence of that, the gravitational Hamiltonian, this is something, a very trivial calculation for many of our colleagues. And you can keep writing down higher and higher order terms, including H bar. And colleagues like Zui, Bird, and others, they have gone up to, I think, C to the power 7 or even higher order terms. So but the bottom line here is that if gravity is inherently quantum, so the change in the gravitational energy is an operator. It can act on some vacuum. And as a consequence, what will happen is that it's going to mix your states from A and B. The positions, operators, momentum are operators, everything is an operator. So inherently, you know that at the end of the day, these things depends on the off-shell nature of the graviton, which you can compute in any theory of perturbativity. You can compute any theory of gravity. Not going into the details here, it's just to show one slide, but coming back to the entanglement. So as I said, that you assume this to be a harmonic oscillator, this to be a harmonic oscillator. So even at the lowest order term, which you are sensitive to in an experiment, you can see that the entanglement builds up because of the cross term between this operator and this operator. So this comes from at this order 1 over d cubed, where d is the distance, intermediate distance between the two systems, quantum systems, and immediately shows that you can build position entanglement. And similarly, you can repeat the same calculation for, okay, so just to finish the story, you can write down in terms of harmonic oscillator states, operators A and B dagger, and you can compute also the wave function evolution, you can compute the concurrence entanglement, or you can compute the entanglement entropy, whatever you want, you can compute. It's a very trivial exercise, nothing very fancy. And for concurrence, you need to satisfy this criteria to be entanglement, which you can satisfy by playing with these numbers. You can take M and D and omega M. Omega M is the frequency of the oscillators, such a way that this is greater than 0 and less than square root of 2.
Wait, so omega M is your harmonic oscillator frequency?
Yeah.
And what order of magnitude is G experimentally?
Oh yeah, this is curly G.
Yeah, curly G.
So that will depend very much on the mass you choose and omega M you choose. And yeah, I will come back to these numbers too very soon. So because these are the numbers.
What was capital C? What is capital C?
Oh, sorry. Yeah, I forgot to perhaps. This is the concurrence. So concurrence you can define by, so concurrence is very useful tool, similar to basis independent witness. So usually we, in our literature, we always use von Neumann's entanglement entropy, but you can also use for bipatcher system. So if you have got a very simple bipatcher system, for that you can use this criteria as well. And so there's your states will be entangled, the bipatcher states, if you satisfy this condition. So that's a very simple definition.
If C is not zero, they'll be entangled or
C has to be bigger than 0 and less than square root of 2.
so any number between there indicates entanglement?
Entanglement between the two bipatcher systems.
I see.
I mean, you can compute also the von Neumann's entanglement entropy. It's just sometimes it's easier. That's the that.
But in this formula that you wrote, it looked like C could become arbitrarily large, depending on the values of those parameters.
Absolutely, yeah. So you know
Does that
exactly.
mean that there's not entanglement? GM over d cubed m squared is big?
So exactly, it's a kind of like limit which perhaps you will come back to the point where the quantum fluctuations become so small that you are effectively becoming like a classical system. So the delocalization parameter, because all these omega m and all will change your 0 point fluctuation. Oh, here it is. So this will change the 0 point fluctuation of these systems. So they become inherently classical. So in the limit when you see the delta xb vanishes, your entanglement will go away. And that happens here. You can see from here because it's the cross term which is important.
Well, I think Clay's worried about C getting too big.
Sorry?
I mean, what's bounding C by square root of 2 in that formula?
So what will bound here is that, I mean, so the point is that you can always find some parameter between m, d, and omega m to satisfy this criteria. Of course, that you can always find. I mean, now the question is, if you go beyond that.
Is little g small for some reason? Are you doing some perturbative series in little g?
Yeah, absolutely. I'm doing this with perturbative calculation, small g. Absolutely. So, but so this is a perturbative calculation. So on top of that, you will have corrections on your wave function. You keep adding higher order corrections. And the other example, which I will show you where we could solve it exactly, but that was a very specific case.
Even if little g is small,
I'm sorry.
it's still going like 1 over a tunable frequency, right?
Yeah, but you will see, you'll be surprised that
C seems to be dimensionful. Is there a typo in the?
Yeah, maybe
Is there a
that's what-
typo in the formula for C?
Is C meant to be g up to a factor of root 2?
okay, so g omega m squared, let's see.
But little g,
Yeah, little g looks dimensionful already.
root 2 isn't the problem, it's the exponent on, it's the exponent on omega.
Yeah,
Okay, I'll check that, maybe.
yeah.
your little g is dimensionful, right?
That's-
The curly g.
This one is
Is that supposed to be dimensionless?
not really, not necessarily.
I think
Have a dimension.
Well, it's not the way it is.
I think script G over omega m, which is like big C up to factors of square root of 2 is dimension.
Yeah, that's dimensionless.
This is dimensionless quantity. But anyways, I mean, it's not so important. I mean, we can check the numbers, but what is important here is that you can arrange some parameters, and you can also check the momentum entanglement, and you can build up like this because it's a perturbative series, so you can build up higher order momentum. If you compute even higher order terms in a coalescing black holes and imagine that very extreme case that the black holes are quantum systems, you can compute the entanglement through this. So it's just what is inherent, what is important is that the mixing between the two quantum systems.
So are we talking about macroscopic objects now? What are we talking?
Yes, now we are talking about macroscopic.
So they're very far from the vacuum.
Yes.
So are there coherent states here somewhere? Or what are we doing exactly?
Yes, so now I will come back to the point that what kind of systems are we going to play with now. So this is exactly where you are hitting the jackpot. So what kind of system should we play with where we can verify this kind of entanglement? So in order to do that, so you would need some quantum system. So here I have got system 1 and system 2, and so I'm placing them in a spatial superposition. So delta X is by special superposition. So it's highly non-Gaussian state. To answer your question, it's a not coherent state, but highly non-Gaussian state. They're sharply peaked at these two spatial positions. And you want to understand non-classical correlation. So you want to understand the entanglement at the end of the day between system 1 and system 2. They're separated by, say, distance d. And this entire experiment, you can do it in a chip. So chip is as big as your iWatch chip. So that's the whole idea. So how big the system should be? So the system, the size of the system should be roughly around, so this is a cartoon diagram of the one which I showed you, around 10 raised to minus 14, 10 raised to minus 15 kilogram. Delta X, the separation here is around 10 to 100 micron, and the interseparation distance is something like 500 micron, and you allow them to interact for roughly around 1 second. Now, what these parameters buy you? So these parameters, for these parameters, the entanglement phase, which is roughly given as I've showed you. So these are my entanglement phase. From there, you can read it because these are the terms which will mix. Yeah. So, for instance, these terms, and combination of these phases will give you roughly order 1 entanglement phase for these choice of parameters. But that's not sufficient because you also have to compute witness. And when you compute the witness, you have to take into account of the effect of environment. So effect of something called decoherence, how well can you maintain the quantum system, and that will change the answer according to the rate at which you can keep the system pure enough. So it goes away from the purity. So if gamma is 0, then you're in the perfect ballpark, but we know that we can never be in a pure system in an experiment. So there will be a decoherence which will destroy the coherence of the system. And then you compute your trace of W rho. And if it's less than 0, then only you can conclude that the two systems have entangled purely via gravity. But having said so, it's extremely, extremely hard because one of the biggest background is your electromagnetic background. The challenge is, how do you get rid of that electromagnetic background?
Well, what about the classical gravitational?
Yeah, I was about, yeah.
Yes, I know, absolutely
The
correct.
same frequency, how can you
Yeah,
tell? Why
absolutely.
are the virtual?
Absolutely correct. So these are gravity gradient noise that you need to understand extremely, extremely well, roughly at the 1 hertz, which is extremely challenging.
Yeah, isn't that many orders of magnitude more than?
The LIGO, yeah, absolutely. So how would you do this experiment? So now the challenging part starts from here. How you're going to realize all these things in an experiment. So far it was just this, simple pen and paper calculation, but the real physics starts now. On top of that, even if you take systems to be neutral, you're entangling via your photon interaction, dipole-dipole interaction, Casimir interaction, which is a 2-photon exchange diagram. And that will generate your potential, which is 1 over r to the power 7. And this is the place where actually Andy came in because in the beginning, we did not take into account. And our collaboration increased. And as we increased, our colleagues from experimental colleagues pointed out that you need to take this into account in your real experiment. And thankfully, the parameters which I showed you, the parameters which for the 10 raised to minus 14 and delta X and D, you can compute the Casimir for a system like diamond, and I will tell you why we are playing with diamond. It is at least 10 times the gravitational background. But it's not only it's not sufficient. You really need to compartmentalize the two systems. You need to have you have to shield it electromagnetically. So the magnetic field of lines cannot penetrate from system 1 to system 2. So you require superconducting sheets as well as a very fine conducting sheet to separate the two systems. So you need to do many, many things to shield your background.
So these are 2 tiny diamond chips. You put them into superpositions, and then you want to entangle gravitation.
So that's the challenge. Very similarly, okay, so you would say that
Doesn't the geometry? Are these spherical chips? How well?
even that we need to manufacture completely from scratch, because there's an amazing amount of understanding how would you even create the superposition. Because so far, no one has gone this level of superposition, and that is itself. So first, we are computing how would you create the macroscopic superposition. Based on that, we need to manufacture our chip. So it will be like a 3D design, which we need to construct.
So these are like qubits on a chip, which
Uh,
are now, which they have, right?
The chips will give you the current. There's a current carrying wires,
Yeah.
and they will generate your magnetic field and the gradient. But the diamond is the system which we are choosing. So
And that's
example,
the thing.
yeah, and why diamond? Because I'll come back because diamond has a defect. Every diamond will have a defect, and these defect will be my ruler. And I will measure those, with the help of those defects, I'm going to measure the spins system. That's the way it will go. So, but before that is another exciting experiment which I want to share with you. There's something, it's a very recent development, but we thought that, okay, we could go, we could do all these things in the laboratory. Why can't we do the similar experiment as light bending experiment? So it is possible to do that. So it's a very simple one graviton exchange between photon and matter, nothing very fancy. But now what you see is that you get an entanglement between the position of this system, which is in the ground state, and imagine this to be your coherent state, very highly occupied photon beam. And you're entangling the position and momentum as a consequence, and this is the basic interaction. So omega is the frequency of the photons, and R is the separation, D is the girth of radius of the cavity. And you can actually put some numbers behind it. You can compute again in a very simple manner. You can compute the algebra with the effective interaction. So this is really the effective interaction now. You can compute the entanglement just to get how big entanglement do you want. And to put some numbers, so you want the size separation to be roughly around 1 meter. So this separation is 1 meter, R. The mass is around 10 kilogram system. The frequency of these, the photon is roughly 10 to 15 hertz. And you can compute the intensity of the photon. And that intensity comes around to be roughly 10 to 24 watt per centimeter square, which is less than 10 to 29. And 10 to 29 is an interesting number because that's the energy where you start having Schwinger pair production. So it's below that. And thankfully, next week, I'm going to meet Donna Strickland, who has really championed this state of art. They are the ones who created this very high intensity beam in a laboratory. But now the challenge is that how you're going to put it in a cavity. And that's the challenge which we have to meet.
So there is a beam at that intensity already.
Yeah, people are talking about, even America has, every major industrial countries have now petawatt laser.
Yeah, but they don't go in circles.
They don't go circle. That's the biggest challenge. They're just one shot experiment.
Yeah.
Now the challenge for us to somehow bend it and put it in a cavity.
We also do it fast. The petawatts are really short pulses.
Short pulses, yes. And I need to get the large occupation number.
Sorry, can you explain again, what exactly are you trying to measure here?
So here, what I'm going to
Is it a
measure.
frequency shift experiment? or-
No, so I want to measure, you can do that, but it's extremely tiny because you see that the angle which you will get is unmeasurable. But what you can measure here is the entanglement between this quantum system and my photon. And how are you going to measure that? So you can build the protocol. So we have built that protocol as well, and I'll tell you soon. It's like a quantum-optomechanics. So anyone who is doing quantum-optomechanics can immediately follow through this argument. You have a question?
Are you thinking of like the very big thing, like as a LIGO mirror or something? That
Yes, exactly, 10 kilogram mirror. And LIGO has recently, that's what they're aiming to do. They have they're taking 10 kilogram mirror and they are trying to cool the 10 kilogram mirror to the ground state. So that's the biggest, one of the things from the matter sector, maybe we can learn quite a lot from the LIGO, and if the LIGO is successful, then maybe at least this part we can understand better. But the remaining part of the challenge is that how do you really take this high intensity beam, put it in a cavity? That remains challenging.
Why does it have to go in? I mean, you put it in a cavity.
Yes, because you want to build entanglement. So you want to let it circle around for a while so that your entanglement entropy increases.
If you just had a straight cavity, you could go by the mass.
Yeah, exactly.
Yeah, you can do that also. Yeah, you can keep it
And that's
bouncing back and forward. Either way, you need some mirror.
Two ways, yeah.
You can do that as well. So we just for as a demonstration proof, we just took it circle, but in principle, you can also to take this just bouncing back and forth. That would be also possible. Yeah, absolutely. So this is another interesting, and why this experiment is interesting as well, because as you know that when you are in 4 dimensions, the graviton has a spin 2 as well as a spin 0 component, and you would need both the components to have a coupling between graviton and photon, because h mu nu, g mu nu. If it's just the h mu nu, a purely a scalar quantity, then trace of photon will be 0, so ht will be 0. Effectively, there is no coupling if the gravity is purely scalar quantity. So inherently, the spin 2 nature comes in this kind of example. Of course, I mean, we have seen spin 2 nature of gravity even in gravitational waves, no doubt about that. But this is an entanglement-based experiment. That's something interesting.
I still don't quite understand what you actually measure in that experiment.
Yeah. So you're going to measure the you're going to measure this entanglement entropy.
No.
Or entanglement.
Well,
I'm computing entanglement entropy.
That's
But
something you can compute
you can
theoretically.
compute the quadrature. You will compute the quadrature. And just to satiate your thirst, I can show you the.
I think he's asking what observable.
Oh,
Yeah.
so yeah. So you are going to measure exactly. So maybe this will help you to. So this is your. Imagine this is your. So in this, I really followed your suggestion that take a laser beam going back and forth, This is your mirror. This is your laser beam. You couple the laser beam to a photon, another photon which talks to this, and you put this one in a cavity, in a photon cavity. So your output is photons coming here, and you are building the correlation between these 2 photons. So it's called something called in quantum optics known as quadrature. So you have Stokes parameters essentially. So with the help of Stokes parameter, you want to see the correlation, and there you want to see whether the 2 systems, the 2 photons, have got entangled or not.
What are the scales of this experiment? Like, how big is R?
Oh yeah,
How big is that beam supposed to be and things like that?
So R is roughly around a meter size, but of course we can scale you. I mean, now you have to optimize the systems and all. So we have taken in this just order of magnitude calculation we have showed you, roughly around a meter. This size of the width is around some centimeters square, I think I've taken, and the intensity was around petawatt, so 10⁻²⁴ watt per centimeter square. But now the challenge is to, I mean, not the challenge, but you want to optimize these numbers. You can try to bring it down and try to still see that, let's say in 10 years, 20 years time, we can do this experiment or not, given the fact that the LIGO is trying to achieve this.
What's special about the matter in the middle? I mean, there's matter everywhere. Why is only that matter contributing to the entanglement phase?
Very good question. Yes, you need to compute as all the couplings. You are asking very, very beautiful question. So in principle, any matter, if it's quantum matter, would entangle with the system. So now you have to put constraints on how, what is the strength of those interactions, whether they are classical or quantum. You need to take care of everything. So you're asking absolutely beautiful questions. And in our paper, actually, this paper, the supplementary material is bigger than the paper, because supplementary material has some of these answers precisely you're asking. So what it means is that these couplings, so so this is a gravitational coupling, the one which I showed you, the coupling between matter and photons have to be computed, and we have to make sure that the mirror does not entangle with any other mirrors. So we have to make sure all those things.
Is this meant to be space-based at the end or ground-based?
Sorry?
Is this meant to be a space-based experiment?
No, again, this will not be it will be a tabletop. We want to do everything on Earth precisely because we want to build statistics. We can keep the system alive for as many runs as possible, so that at the end of the day, I mean, one experiment, one shot will never give us anything. It will just be a background. So you want to get 95, 96% confidence level. It's like we want to make it like LHC.
Can I make a mundane experimental comment? So,
Please.
so the state of the art for LIGO-like cavities is about 1 megawatt per square centimeter. So it looks to me like you're short 18 orders of magnitude.
No, we are short. It's a good point.
Yeah.
So what you need here, because I was just trying to, so you see that the frequency. So you want this mirror, the mirror which I was showing you, 10 kilogram system, has a very, very tiny frequency. So this is another challenge. So this is a harmonic oscillator trap. We are trapping this 10 kilogram system, but it is at 10 raised to minus
You do
9
the
hertz.
measurement at that frequency.
The frequency which I'm going to measure.
And I thought,
is-
isn't the I there, isn't that the laser power
Yeah.
flux?
That's the
And
idea.
I'm telling you that 10 to the 6,
Mhm.
not 10 to the 24, is what they can actually build cavities.
I know, cavity is, that's true. So there's a huge challenge here. To build the cavity and build the, you need to really
Okay,
champion this. Yeah, I absolutely agree. Yeah.
okay.
And this is one of the reasons I'm going to meet her and ask whether we can do something about it or not.
I mean, you can get very high powers,
Yeah.
but just in a little spot, like at Livermore, where they're.
Absolutely, yeah.
But you can't get a.
You cannot get it. Right now,
And that's just the
technology is-
fraction theory. You can't make a beam.
that technology is still not there for us.
Okay.
That's something which we need to develop, but it has many applications if we can manage to do that. Someone had a question. Yes,
So-
please.
This is like related to Clay's question. So you expect that you can tune the intensity and then you'll see how the quadrature changes?
Exactly.
Subtract the background?
Exactly. Yeah.
Okay.
So it's just a cavity quantum-optomechanical protocol, the one which I showed you the diagram.
Yeah, how are you gonna isolate the massive backgrounds?
Oh, yeah, this is absolutely very, very beautiful question. Let's come back to that. So many, many beautiful challenges. There's no dearth of challenges, and some of the challenges which I cannot even write it down because maybe in the process I can see perhaps we have all been thinking about BSM physics. Maybe there's action, there's a hidden photon, you can anything, you name it, anything can lead to unknown interactions can lead to interact with the system and entangle the system. So you see that, but the known ones, let's call the known ones, there are many challenges. So we need to prepare the system. We need to avoid exactly like various decoherence. And not only that, the question which Chris and you have been asking me, how do you get rid of the noise, gravity-induced noise? These are gravity gradient noise, the relative acceleration noise. So even a serpent slithers or a butterfly, forget serpent is very big quantity. Even a butterfly flies by me, it will induce a phase and destroy the system. So I need an exclusion zone. So this is something which we have computed it. Thankfully, I mean, Kip Thorne had been worrying for these kind of questions from ages because of the LIGO experiment itself. So anyway, just to, depending on how much time I have, but I can,
For 5 minutes.
oh, okay. I can briefly just allude you towards some of the experimental challenges we have. So you need to, as I said at the beginning, you need to really create the system in a perfect, as much as possible to a ground state. And you want to disturb it very tiny because you are measuring something which is the relative acceleration between these two systems is roughly 10 raised to minus 17 meter per second squared in 1 hertz. So in 1 second, the acceleration just between the two systems, if you exclude everything, is roughly 10 raised to minus 17 meter per second squared. That's the kind of sensitivity you want to reach. So you are really trying to prepare as much pure system as possible. Anything you tell me you will destroy. But nevertheless, our colleagues have managed, for instance, Andy's colleague is Jerry Gabriel's, his technology has gone into creating the LHC. So trust me that in LHC, where they collide this proton-proton, perhaps Liang Tao knows that, the vacuum is amazing. 1 part in 17, 1 part in 10 raised to 20 Pascal. Effectively, there's not even a molecule hiding there. At that point, I mean, you cannot talk about a vacuum as such, because there is no molecule left. So that's the kind of vacuum you need. I mean, to create this kind of experiment. But that's the one part. So you need to compute all the decoherence rates, scattering, and all those things you need to compute. I'm not going to the details, but if anyone wants to know, ask me later. You try to put some numbers, the decoherence rates versus temperature, how cool the system has to be. So you want to go for cooling as small as possible, something like 0.1 Kelvin. So the external temperature, so imagine you have, this is your experimental box, you have created a superposition, this is the pressure which you would like to operate, 1 part in 10 raised to 15 Pascal, the temperature, external temperature has to be roughly 0.15 Kelvin, and the temperature of these systems, roughly around millikelvin. It's just from the phonon vibrations, which you have to tame that as well.
Okay, but you're gonna pump a petawatt of power into a system at 0.1 Kelvin.
Sorry, but
You have a petawatt laser.
Oh, no, this one is
No,
not with
that's
the
a different
laser.
experiment.
It's a different.
Oh, okay.
This is the one about macroscopic
Max.
superpositions.
Yeah. A petawatt laser has its own challenges, and I will show you. I will show you, just to give you an example, that because, you know, we want to do it on Earth because we want to build statistics. And that depends on your decoherence rate. You see the decoherence rate, for different decoherence rate, you need different number of runs. So if you can tame up to say 1 pound in 10 raised to 2, something here, let's say, fairly close to this number, then the red one, you see that you would require roughly around 1,000, 5,000 runs. So you have to build statistics, you have to do this kind of quantum simulations to build statistics. You say that if you want to get 95%, 90% confidence, how many runs you want to do. And keep in mind that if I do the run in say 1 second, and if I have 1,000 runs or 5,000 runs, it will easily take me half a month or so to get to build up statistics. And if my decoherence is worse, then you see that other extreme end, where the decoherence rate is 0.1, I would need this many runs. And if I multiply that even with 1 second, it will take more than a year to get 95% or 90% confidence level that I've seen something. So these are hard experiments, but fun experiment. Coming back to your point, for the cavity kind of experiment, this matter has to be, again, you can compute the decoherence rates. The known ones, unknown ones, I cannot, suppose if there is axion hits, I cannot really say much because I don't know the coupling of the axion. But maybe, hopefully, if it does, I will come to know new particle. That's also fun part. So from various gas collisions and the vacuum and the temperature, so you really have to go. So just to give an example, for 10 kilogram system, you want to measure the entanglement. So the entanglement is order 1 within less than 1/10 of a second, because 0.1 hertz I'm operating. And for that, I need to go to even extreme pressure, 1 part in 10 raised to 25 Pascal, and the temperature is around millikelvin or so. That's the kind of requirement we need. And then you can do many things. I do not have much time. You can do tomography. You can look for just one plot, maybe, because some of our colleagues, I know that many of us are interested in axion here. One time or other, we have all worked on it. You can constrain this kind of diagrams. So just this is a nucleon, and here you have the axion interaction. Sorry, axion is here, and this is just the photon interaction. So that kind of interaction coupling will effectively generate you a effective potential, and you can try to constrain this kind of diagram. And so for axion, we know that quite a lot of range has been ruled out already, or been constrained, not ruled out, perhaps constrained, very well constrained. But this is the gold part is the one where the experiment which we are talking about potentially can be done. So we can potentially go to even tiny masses in the axion. We don't gain so much in the strength. The coupling we don't gain, but we can gain in the mass of the axion, what we can go. You can do many things, because lack of time, I will not go. One last thing about the gravity gradient noise, and that's the devil. Because gravity itself is its own enemy for doing any gravitational experiment, because the fact of the equivalence principle, the fact that this experiment is not a point particle experiment, that it has a width. So the Riemann tensor here and here, they are slightly different. And that causes a huge trouble for us, because so you have to compute that noise budget as well for this experiment. And this is what we are trying to do. I'll skip the formalism, because it's a known formalism, but I can give you some idea. So for instance, if you want, just to give an example, a jerk have to be away from at least 10 meters from the experiment. Cars have to be roughly around 100 meters, planes have to be 1,000 meters. Seismic noise, you need to, you cannot potentially do this experiment on the surface of Earth, because it's seismically it's very active. You have to go maybe underground. How big your apparatus has to be, whether can you fit it in a kind of drop tower experiment. So near where I live, ZAM is a German facility where they have the drop tower. So at some point we were thinking about, can we fit in our experiment in a drop tower and drop tower capsule, and that's what we were doing, this kind of calculation, that how big the mass of this system has to be, and what should be the size of the system, a box where you are doing this experiment. So you need to do all these calculations. So each and every calculation perhaps will go further into details and effectively will become a PhD thesis, because that's what it amounts to. So here, these are just very order of magnitude kind of calculations we are doing. But what it seems like that maybe you have to go to underground, because the underground is seismically less active. Maybe how deep you go is, I mean, the deeper you go, better it is. You have to embed the capsule in various levels, because each and every level will have a different levels of vacuum, because you want to protect the system as much as possible, even from jitter. Even a small jitter can destroy and give me the external phase, which we have been talking about. So some of these things we have kind of got some idea, but we need to go even further in these directions. I'm skipping the fact, a very interesting part that I think Sam was asking me, that how would you create this superposition? And not know, maybe I should wrap. Yeah, okay. So yeah, there's a new way of creating the superposition. How big can you go? So please ask me if you're interested. So this is something which we are working on, various groups are working on, how big the superposition. There are many things involved. There's something called the spin Humpty Dumpty effect due to English, Scala and Stringer. Stringer has worked even in this area as well. It's about not only meeting the position and momentum of the two systems, but you have to take care of the spin, whether the spin overlap sufficiently or not. And here comes the problem with the condensed matter aspects as well as many other things. Just to give an idea that you need you cannot tolerate even a tiny fluctuation in the current. The fluctuation in the current which generates your magnetic field has to be less than 1 part in 10⁻⁻10, 1 part in 10⁻11. That kind of accuracy you are looking for. Because even this tiny fluctuation in the current will generate you a fluctuation in the magnetic field that will talk to the defect and destroy the coherence. So that's the level of challenge you're talking about. Very prototype experiment has been done. This is exactly the one which I was talking about, two particles in a Stern-Gerlach setup. So this experiment has been done in Israel with our colleagues. Ron Foreman is the lead experimentalist. He's in Kettler's lab in MIT right now. And but it's a very tiny system. Rubidium atom with 10⁻26 kilograms. And I have to go 10, 12 orders of magnitude in mass. So a huge, tall order. But nevertheless, it sounds like a fiction, science fiction, many of us. But tomorrow is going to be reality. And hopefully we'll be able to do this kind of experiment, not say in 5 years' time, 10 years' time, maybe 20, 30. That's the time scale I would be more realistic. We can do this kind of experiment. Amazing amount of ground state control of the system, which will teach us many things, even including perhaps quantum computing aspects. Excellent levitation device, one of the best vacuum you're talking about. Everything what you're talking about is the best. No one has achieved so far. So that's the kind of like hunger we have. But of course, that brings tremendous amount of challenges to deal with. Innovative material science, and at the end of the day, if you can say something about this entanglement, that will be perhaps, will be indeed very beautiful. So yeah, it's a community effort. I mean, we cannot do it just by myself or anyone. It's really a community effort for young colleagues, ours. They have, they are the ones who will reap the harvest from whatever we are trying to do right now. They are the ones who are going to see this experiment through. So please join us, contact me. I'll contact Andy or even Jane and Gautam. They are also very much interested in these aspects. And so yeah, thanks. Thank you very much. I have reached my excess time, so let me thank you. Myself.
You have time for 1 or 2 questions?
I think I don't understand the light bending.
Okay.
Could you go back to
Sure.
the slide or one of the slides? So the mass in the center, it's in a superposition.
Yeah.
What is this?
That you want to keep a quantum system. So imagine that to be your harmonic oscillator.
But what is the superposition exactly? It's not a spatial superposition.
It's a 0 point fluctuation. So it's given by
it's just
omega. Square root of h by 2m omega. This is
so it's just in the ground state.
Yeah. And so it's governed by your omega m parameter. That's what the width will be.
Okay. I see.
Yeah. So you're playing with the Gaussian state. If you want, you can play with the non-Gaussian state. But if you take a 10-kilogram system, PhD in non-Gaussian state is very hard.
Yeah.
So that's the reason we have gone to Gaussian.
Wait, but that one is actually petawatts, right?
Yeah, the frequency of this, but now we are trying to reduce that. We are now trying to go for optimization. So the parameters, I think maybe I have a plot here. If I'll show it to you. You can go. I'm skipping quite a lot of things time, but yeah. So this is so we have done the optimization also. So we can go down all the way to 10⁶ watt. So something which you were asking me, and that because this is what we know. I mean that something achievable. So we wanted to go to this range, and for that range, you don't get a very large superposition. So for instance, the red ones match with the red ones. So for 10⁶ watt, the delta R, the 0-point fluctuation will give you a delocalization of roughly of order of 30 micron. For 10⁹ watts, 10 micron is sufficient. And the frequency which you have to play with is roughly 2.5 hertz. So this omega m has to be 2.5.
How did you suddenly achieve this massive?
Very good question.
Order.
Squeezing. So in the one which I showed you, I didn't really utilize. I didn't want to complicate the life, and I didn't want to squeeze the system. But now how you achieve this, because you gain this factor, exponential factor. So what you do is that you try to squeeze it exactly like what people do for quantum optics experiment. Now you can ask the question, how much squeezing do I need? So xi has to be roughly 20 to 30 orders. Right. So that's a huge amount of squeezing.
Right.
So you
can do maybe one right now.
You see that in experiment, what we are learning day by day is that we can never be accurate. And if I try to solve one problem, I am bitten by other side of the problems. So the problem which I have to pay now is to squeeze. I have to keep squeezing the potential 30 times to generate these kind of numbers. But it's kind of like feasible. But I mean, this is just we are building this kind of various protocols. But
Squeezing at that level gives you exponentially increasing noise.
yeah, so you need to take care of this noise and decoherence, everything. You're absolutely correct. So some of these things we need to work out and figure out how much we can tolerate, and also.
Right. I mean, I get why you're going for 10⁹ because that's about what you can control cryogenically, but.
Yeah, I mean, many challenges, and but that's the fun part, that we think that maybe not immediately in 5 years' time, but 10, 20, 15, 20 years is the ideal time scale where we are hoping that we can do this kind of things.
No more questions. Let's bring the speaker again.